One of the things we are going to need to be able to solve equations involving exponential and logarithmic functions is some properties of logs. That is what we are going to address here, because ultimately that is our goal, is to be able to solve equations involving exponential and logarithmic functions. Objectives here: use the product rule, the quotient rule, the power rule. Expand logarithmic equations, condense logarithmic equations, and use the change of base rule. First, the product rule. For m greater than 0 and n greater than 0, log base a of m times n is log base a of m plus log base a of n. What this really comes down to is the rules that we have for exponents. And I'm not going to go into exactly why and develop this fully, but just remember that a to the m times a to the n is equal to a to the m plus n. And remember that logs are exponents. And so that's sort of the reason for where this comes from. I'm not going to go into the full development of it, but that's just a property we have for exponents, so I wanted to bring it to your attention here as why we are now adding. An important thing is that log base a of m times n is not equal to log base a of m times log base a of n. Product inside a log does not mean product of logs. In this case, this will break down into log base 3 of 3 plus log base 3 of x, using that property. A product inside a log can be separated into two separate logs with addition between them. Log base 3 of 3 is 1. If I want to simplify that, if I can. 3 to the first is equal to 3. That's the product rule. Let's take a look at the quotient rule. Log base a of m divided by n is log base a of m minus log base a of n. So when you have division inside a log, it can be separated into two separate logs, separated by subtraction. This first one would be log base 3 of x minus log base 3 of y. Notice the base stays the same on the two logs. This one is just a condensed type problem. This would be the natural log of 2 over x going the opposite direction. When you have two logs separated by subtraction, you can condense them into a single log with division inside of it. This will not simplify. A log divided by a log does not simplify just using properties of logs. Power rule says that the log base a of m to the n is n times log base a of m. This comes from the product rule over and over again. Basically, if you have m to the n, that's m times m times m, n times, and you can break that apart. If you have m times m times m times m, you would be adding the log m log base a of m little n times. So that's where that comes from. An important thing here is that this exponent has to be on the m, not on the log itself. This is 2 log of x. Oh, shoot. Did I forget my base when I typed this up? No, if there's no base there, it is 10. So this is 2 times log base 10 of x. That's the common log. This example asks us to use those properties to expand these expressions. One thing you could do here is you could multiply 9 times 27, and that's like 243, I think, and then figure out what log base 3 of 243 is. But that's a big number. the 243 to work with, I would much rather use my property of logs to rewrite this as log base 3 of 9 plus log base 3 of 27, and then say log base 3 of 9 is 2, because 3 squared is 9, and log base 3 of 27 is 3, because, so we're using this idea. 3 squared is 9, and 3 cubed is 27. So you're looking for that exponent, right? So the answer here, this simplifies all the way down to 5, which is what you would get if you did log base 3 of 243 and then realized that 3 to the 5th is 243. You'd get that exponent. But you may not realize 3 to the 5th is 243. This one with variables, you can't really do much simplification of the numbers, right? Let's break this apart. First, we would need to separate this into 2 separate logs with subtraction between them because of the division. So you want to do that division first, because remember, a fraction bar is kind of like is like a set of parentheses. It comes first in the order of operations in the PEMDAS. It puts parentheses around the numerator and the denominator. So that's why I did that one first. Now I have the natural log of 2 plus the natural log of y for this first part because of that product. So that's what that breaks into. This one is going to be the natural log of x plus the natural log of z squared. Product will break into addition between 2 logs. Natural log of 2 plus the natural log of y. I'm going to distribute the the negative. I'm also at the same time going to recognize that this 2 right here can be brought in front as a coefficient of that log of z using the power rule. So now I have fully expanded this original natural log that I started with. One thing that I do typically do, instead of doing this step where I have to distribute that negative, I'll recognize that anything that started in the denominator, this xz squared all started in the denominator, and the 2 and the y started in the numerator, the things that started in the numerator are positive coefficients. The ones in the denominator have that negative coefficient to make sure that the idea of keeping them in the denominator. Let's try that on the next one. Maybe we can use that shortcut. First, I'm going to write this as log base 5 of x squared y over 25 to the 1/3 power. A cube root is the 1/3 power. I'm going to bring that 1/3 out because it is on this entire thing. And now I'm going to have 1/3 times, when I try to expand this, I'm going to put log base 5 of x squared plus log base 5 of y minus log base 5 of 25. Using that idea that the stuff that was in the numerator is the plus and what's in the denominator is the minus. The 1/3 has to be times that entire, all 3 of these logs, since it's times the single log above it. I also can use my power rule on this x squared and bring the 2 in front. So this will be 2/3 log base 5 of x plus 1/3 log base 5 of y, distributing the 1/3. And then here I'm going to get just 2/3. The reason for that is that this guy is equal to 2. 5 squared is equal to 25. So when I distribute the 1/3 to that 2, I get negative 2/3 there. Okay, that's expanding these logs. Many times to help us solve equations, we actually want to condense them. So we're now going to go the other way. This is where using that property that we talked about before, or not really a property, but the idea that anything that has that positive coefficient goes in the numerator and the negative coefficient goes in the denominator, can help you to pretty easily see that the 4 and the y are going to go in the numerator of the condensed form and the x in the denominator. If you need to see it, the actual steps using the properties, if we bring those first two together, we get 4 over y. 4 over x. And then when we combine those, that's going to be a product. So that's how you get it actually using the properties, sort of one at a time. Let's write this as log of x squared plus log of z minus 1 cubed, making sure we recognize that the cube goes on the z minus 1 minus log of y. One thing to be very careful of here, the temptation might be to make this 3 times log of z minus 3 times log of 1. That is not correct. Never ever can you separate addition or subtraction inside a single log into two different logs. If you have two different logs added or subtracted, then you can combine them into a single log. But not addition or subtraction inside a single log. You can't do anything with that. Now I'm going to condense these into x squared times z minus 1 cubed, and then that minus log of y will end up being in the denominator of that. Notice I had to bring up the exponents first, the coefficients to be exponents first, and then I was able to condense the logs once I just had logs added and subtracted. One more here. You can follow order of operations. Inside the parentheses, we're going to be able to condense the log base 7 of x minus log base 7 of y into log base 7 of x over y. This 2 is on both of those, so the whole thing there is squared. You might, if you prefer, simplify that fraction inside there to x squared over y squared. Both of them are squared. Same result you would have gotten if you had distributed the 2 first, brought the exponent up, and then condensed that down into a single log. Okay, one more here. I am going to take this, they're all the same base 10, and condense this into a single log in one step. Whoa, is that too much? Let's talk about how I did that. Positive log of x plus log of x squared minus 4. Both positive coefficients there on the logs. Those went into the numerator. These two are both negative. They go into the denominator. If you prefer to really understand why, you could factor out a negative out of the last two so that there's addition between them. When there's addition between them, they become a product. So these two would be log of x times x squared minus 4. And these two would be log of 15 times x minus 2. because there's addition between them when you factor out the negative. And now a negative between those two will condense to division inside a single log. Okay, I'm not done though, because I want to simplify this as much as I can. X squared minus 4 factors into x minus 2 times x plus 2. We have 15 times x plus 2. So let's go ahead and simplify those x plus 2's, those common factors, to give me log of x times x minus 2 all over 15. Do not act like you can bring that 15 out in front. This is not log times x times x minus 2 over 15 such that you could, factor something out. It's not a product, it's log of that. One thing I try to remind my students, you can never just write log with nothing following it. It's kind of like writing a square root with nothing inside of it. You take the square root of something. You take the log of something, okay? So don't be tempted to do something a little funny like just write a log. I never want to see something like log equals 6. That makes no mathematical sense. Log of what? Okay. One more thing we can look at here, and it'll be our last thing in this section, is our change of base formula. This is helpful when you have a base other than e or 10, because your calculator will only do base e and base 10 easily. Scientific calculators definitely only are going to do base e and base 10 easily. Graphing calculators can sometimes do base a, but it requires going into the catalog and finding it. So this is pretty helpful. One thing I should make sure you're aware of, a long time ago, before we had calculators to do things like approximate that natural log of 5 that we did, there were books that literally just had tables and tables and tables and tables of all different logs. Like, what is the value approximately of the natural log of 5? Or the natural log of 5.1, or whatever. And it would have those in tables instead of just being able to put it in your calculator. So consider yourself fortunate that you're not living in that time, but we still can use this change of base formula for helping us use our graphing our calculators a little bit more easily. We have all these conditions here. M, of course, has to be greater than 0 because you have to have a negative. You can't have a negative inside a log. You need the base to be appropriate. Log base a of m is equal to log base b of m over log base b of a. You may be like, wait, where did b come from? Well, you pick a convenient b. Pick something that's nice. What are nice, convenient things on our calculator? Sorry, that's messy. I want to rewrite that. E, base E and base 10 are both very common things to use, and they are also easy on your calculator. So we could say log of m over log of a, where we're talking about the common log, base 10. We could say the natural log of m over the natural log of a. You can use either. I tend towards using the natural log just because I see it in more applications in further mathematics, but both are important and used. Log base 3 of 8. Before we do this, I want to think about what this could be. Approximately, What integers would this be between? I'm asking myself 3 to the 8. 3 to what is equal to 8? It has to be between 1 and 2, right? Because 3 to the first would be 3. 3 squared would be 9. So it's going to be between 1 and 2, and probably closer to 2, because 8 is, close to 9. You could, in your calculator, throw this in if you find that base 3. But for me, I would just put it in my calculator this way. Log base 3 of 8 equals natural log of 8 over the natural log of 3. When we throw that in our calculator, the natural log is here of 8. Close the parentheses, divide it by the natural log of 3, and we get 1.89, which is what we expected. We said it should be between 1 and 2, closer to 2. Let's try, instead of using the natural log, what if we use the common log? Log of 8 divided by log of 3. Same answer, right? It doesn't matter which base you use. You could use base 1 million. Log base 1 million of 8 over log base 1 million of 3 will equal this same number. Let's look at one more example, and before we go to our calculator to do it, I want you to think about what integers this result will be. Oh, shoot. This is approximately 1.89. That's what we got. What integers would be log base 12 of 9? What would that be between? I'll give you a second to think. Should be between 0 and 1. We are asking 12 to the what is equal to 9. 12 to the 0 is 1. 12 to the first is 12. So it should be between those two exponents, 0 and 1. It'll be the natural log of 9 over the natural log of 12. Go to our calculator. ln of 9 divided by ln of 12. Like I said, I tend to prefer the natural log, but there's no reason you can't use the common log. 0.88. These are approximations, remember. These are irrational numbers. Okay. If you recall, when we started this, well, in this section we talked about some properties of logs, right? And at the beginning I said the reason we need these properties of logs is so that we can solve exponential and logarithmic equations. That is what we are going to do in the next section. So be prepared for that.